Right, so hello everybody. Welcome to the last but one London Learning Lean of term. We are going to do one next term, but next week we've got, I'm probably going to mangle their name, but it's mathematicians from Yakima, who's going to talk about implementing cryptographic primitives in Lean. But this week we're very pleased to welcome straight from Imperial College London, i.e. here, Joy and Runchang who are going to tell us about some basics of Gaussian measure in Lean. Over to you.
Hello, everyone. I'm Runchang and my partner Joy Hu will together give some basic presentation about the very simple things in the Gaussian measure this session. And here's the overview of our report. The first is introduction, so basically motivation. How did we start to focus on this part of the Lean? Why do we want to formalize measure theory things in Lean? And the second part is the first four important results we proved in Lean. So last summer vacation, and these four important results were only about the Gaussian measure. How do we formalize it? And some important results about the Gaussian measures only. And the third part is other three important results. In addition to the previous things about Gaussian measure, this part will also add the Gaussian random variables. How do we formalize Gaussian random variables, and some results about the random variables. Yeah, and the last part is some glimpse to our future work and a little talk about the ChatGPT. It's very popular these days, so we are going to give a brief talk about this. Let's welcome Joy to give the introduction about motivation.
So speaking of the motivations, so before the summer, me and Runchang are new to Lean. So actually we know nothing but the natural number game by Professor Kevin. And we were planned to do something related to like the large number, the law of large number, improbability, and some central limit theorem, but these two are too hard for beginners. So we turned to the Zena Discord channel to seek for some help. And Mr. Jason was there, provided us with some good structures of Gaussian measure. And we know something, we know about Gaussian measure during our studying at Imperial. So all we left to do is to replace all theories with some rigorous proofs.
Okay, so before we go to the first four important results, we may give some brief go through about the basic definitions. So the first, our work were very basic, so maybe the definitions given here are quite simple, especially compared to some previous guy who gave the presentation about this. So, well, first, what the measurable space? What is a measurable space? A measurable space, so basically it's a tuple consists of a set and the sigma algebra on the set. This is called the measurable space, and here are two examples. The first example is that the set X contains three elements, and the first sigma algebra on X is a universal set and an empty set, and the first measurable space consists of the set X and sigma algebra F1. The second sigma algebra on the same set but different sigma algebra is a power set of X. So basically, the set of all subsets of X, and X and F2 forms another measurable space, and you can just check the definitions. Very trivial. The second example is real space. So basically, it consists of the set real number and real sigma algebra on the real number. What is a real sigma algebra? Real sigma algebra is the smallest sigma algebra that contains all the open subsets of R. And this is a very common thing and important thing in probability theory or probability relative things. And second definition is measure. So given measurable space we defined previously, a measure on the measurable space is actually just a function mapping the set in the sigma algebra to the non-negative, to the extended non-negative real number. So basically non-negative real numbers and plus positive infinite. And also to be measured, there are two conditions to satisfy. The first condition is a measure of empty set. So basically a measure mapping an empty set to 0. And the second result is sigma. It's called the sigma additivity. So basically for pairwise disjoint countable many sets in the sigma algebra, the measure of the union of these sets equals to the sum of their measures. Here's an example. So basically let X be a set and curly A be a sigma algebra on the X. The measure mu from curly A to the extended non-negative real number is defined to be the cardinality of the set A if the A only containing finitely many elements, and the measure of the A equals to positive infinite otherwise. So basically, if A containing infinitely many elements. And this measure actually has its own name called the counting measure. It's quite follows the intuition, right? And okay, next definition is the Dirac measure. It's also an example of the measure, but it's very important to our later results. So Dirac measure, as before, is a given measurable space set X and sigma algebra A. Dirac measure usually has a the parameter called its X, and the Dirac measure set mapping the set that containing X to 1, and mapping any set not containing X to 0. This is how the Dirac measure defined. Okay, and now we are going to briefly introduce about the Lebesgue measure. We only give its intuition or how to intuitively understand it, but not give its formal definition, because to construct the formal definition of the Lebesgue measure is quite complicated and may take a lot of time. There's no enough time today, and we are just going to briefly introduce it. So Lebesgue measure is you can understand it as the function that gives length or area or volume of a set. So 1D for length and 2D for area and 3D all over. So we call it volume. And we usually use lambda to denote the Lebesgue measure. And here are some examples to understand the Lebesgue measures. For example, the Lebesgue measure of the interval, closed interval from 0 to 1 equals to the closed interval from 2 to 3, and equals to the half open, half closed interval 2 to 3, also equals to 1, because intuitively these three intervals have length 1, right? And another example is the Lebesgue measure on R2. So the Lebesgue measure of this part, this area is 3 times. Oh wait, here's the typo. Should be 3 times 7, right? 3 times 7 should be 21, and the Lebesgue measure of the. It's okay. Oh yeah. Oh yeah. Sorry. I spelled something wrong. So here's right. Sorry. 3 plus 7 should be 10, right? The total length is 10, and the Lebesgue measure of the rational number is 0. Why is 0? Because we know the rational number is a countable in many rational number set contains countably many points, and each point have the length 0. And by the sigma additivity of the measure, the Lebesgue measure of the whole rational number set is just 0, right? And for the Lebesgue measure on R2, this area 1, 2, 3, and times 0 to 3. It's just 2. Its Lebesgue measure is 2 times 3 equals to 6, right? Okay, and here's a probability measure. So probability measure is a special family of the measure. So any measure. So first, it should be a measure, right? And if it's a measure, and it also satisfies the condition that the measure of the universal side is equals to 1, then we call the measure to be the probability measure. And we'll then give a very important result called the rate-iniquitym derivative here. So rate-iniquitym derivative is a definition based on a definition that describes the relation between two measures. So given two measures, mu1, mu2, and there's an f called the rate-iniquitym derivative if the mu1 measure of A equals to the integration of the f over the set A with respect to measure mu2, then we call that's how the rate-iniquitym derivative is defined.
So it's the same sigma, mu1 and mu2.
Yeah.
And f is measurable.
Yeah. Sure.
For which measure? That makes sense. Is that supposed to be measurable for one? Oh, for mu2 because you're integrating. Okay.
Yeah.
Got it.
So yeah. And we see in the previous page that we actually understand the measure as integration. So at least for the Lebesgue measure, we can understand the Lebesgue measure of set A. Just can we understand the integration of constant 1 over the set A dx? This is a quite brief understanding of the Lebesgue measure. And in this sense, the Gaussian measure we'll introduce formally later can be understood as a measure whose rate-iniquitym derivative is a Gaussian function. You know, the Gaussian function is just 1 over 2 pi square and exponential something. You know, the complex thing. Let's see this page. That's how the Gaussian measure formally defined. So the upper one is a formal definition, and here follows an interpretation of the Gaussian measure. You can understand the Gaussian measure as a measure whose rate-iniquitym derivative is Gaussian function, of course, with two parameters, mu and sigma squared. Okay. Oh, and by the way, there's a special case. You know, in probability course, we usually don't talk about the case that the variance of a normal distribution or Gaussian distribution equals 0, but actually the formal definition of a Gaussian measure or Gaussian distribution can have the variance parameter equal to 0, and in this sense, we define it to be the Dirac measure we introduced before. Okay, and here is another definition: absolutely continuity between the measures. So given two measures, mu1, mu2, mu1 is absolutely continuous with respect to mu2, and we denote it as mu1 is much smaller than mu2 if any set, for any measurable set, of course, E. If the mu2 measure of E equal to 0, then we can get the mu1 measure of E is 0. That's what's the definition of absolute continuity.
So here's the summary of our finished work during the summer. Here's the 6 results that we have successfully proved in Lin during the summer. And so the first one is that the Gaussian measure is a probability measure, which is quite simple in math. And the second one is that the first moment measure of the Gaussian process with parameters mean m and standard deviation s is m. That is, in the words of probability, if a random variable follows the normal distribution with mean m and standard deviation s, we said that the expectation of that random variable x equals to m. And the third result and the fourth result are quite similar. So one is to say that the Gaussian measure is absolutely continuous with respect to the Lebesgue measure. And the other one is just to say that the Lebesgue measure is absolutely continuous with respect to the Gaussian measure. And the fifth one just says if the push forward measure of a random variable is a Gaussian measure, then the variable is the Gaussian. And the random variable here should be of the standard deviation of 1 and very mean, which is denoted by m in our proof. And this last one is similar to the fifth one, but in that case, we have a random variable with mean of 0 and denote the standard deviation with s. So now we will talk about the results one by one in details. So the first one, we want to prove that the Gaussian measure is a probability measure. So what we need to do is that by the definition of the probability measure, we need to prove that the Gaussian measure of the entire set equals to 1. So the problem will be split into two parts because of the special definition of Gaussian measure. That is, when the standard deviation sigma equals to 0, by its definition, our Gaussian measure is defined to be the direct measure. And what we need to do is to prove the direct measure of the universal set is 1. And this is really simple when we prove it in Ling, because it's just done by definitions. We just rewrite our measure into direct measures and just everything follows that would be really simple. And the other one is kind of more complicated. So when the sigma is not 0, we need to prove the integral of the Gaussian density function equals to 1. But just in Ling, everything will become more complicated than when we do it by hand. So our problems here is that in Ling, the measure of the set is defined to be Lintegral with an L before integral, which is slightly different to our usual integral. And this is of a function of the type from the real numbers to the extended non-negative real numbers. So although we have a really good theorem called Gaussian integral, which is represented here in Ling, we still need to change from the Lintegral form to integral form, and then change of variables so that we can apply our theorem Gaussian integral here. So how can we change from integral to integral? The command represents here can help us to do the trick. However, this command will split the goals into 3 subgoals. So the first one is evaluate the integral by change of variables first, and then using the Gaussian integral theorem as stated before to do the calculations. And the other two are just to prove this is finite integrable and the integrand is almost everywhere non-negative. So actually, that's why Ling defined it as Lintegral instead of just our usual integral. So when we do it in math, we just usually assume that the Gaussian density is integrable and positive, just not negative. Whereas we still need to prove it in Ling to be more rigorous, I think. These two parts are not very hard in Ling, and so we are not going to talk about it too much. So the hardest part is about the change of variables. We have these theorems in Ling that can help us to do the change of variables, but change of variables is really a hard part in Ling, because in order to use this theorem, we have to fulfill all is prerequisites. That is to say, our universal set equals to the image of the function, the proposition H prime here. And we also need to prove that the function is injective, the proposition HF here. And we also need to find derivative of the linear function. This seems trivial in math, but not that in Ling, as derivatives are defined as linear map or generality to high dimensional functions. So we need to find correct linear map for it, and appropriate function will result to evaluate the determinant of the linear map. And finally, we need to find appropriate results to confirm that the linear map is indeed the result of the functions. So not very hard to understand it, but a lot of works need to do in proving it in Ling. So then comes to the second theorem, that is to say that the Gaussian measure gamma with mean mu and standard deviation sigma, sigma is not equals to 0. The first moment of that Gaussian measure is mu. So actually what we need to do is to prove this integral equals to mu. And if we converted the integral in terms of Gaussian measure to Lebesgue measure, with this substitution here, we can change the integral to this form, and the left-hand side of the equations can be split into the sum of two integrals here. And with the help of Mr. Jason, we can prove that the latter part equals to 0 actually. And all we need to do is to prove that the formal part equals to mu times the square root of pi. And this can be proved by the theorem called Gaussian integral that we have used many times and talk about it before. Yeah. And then comes to the third theorems, that is to prove that the Gaussian measure is absolutely continuous with respect to the Lebesgue measure. So in other words, what we need to prove is that for arbitrary measurable sets E, if we are given that the Lebesgue measure of the set E equals to 0, we need to prove that the Gaussian measure of E is also equals to 0. So some results that already being formalized in Ling can split this problem into some two sub-problems. And one is to prove that the Gaussian density is measurable, and which can be finished by the one-word command, measurability in Ling. And the other one is just to, if we are given a Lebesgue measure of the set is 0, we need to, if we are given that the Lebesgue measure of the set E equals to 0, we need to prove that the Lebesgue measure of that set, of the intersection of that set and the other set still equals to 0. And the math proof are displayed here. And I think these are easy to understand. Yeah. And the third one, as I said before, is quite similar to the fourth one are quite similar to the third one. So actually here we need to prove that for arbitrary measurable set E, if we are given that the Gaussian measure of that set E is equals to 0, we need to prove that the Lebesgue measure of E also equals to 0. So the ideas here is that we need to prove that the Lebesgue measure equals to the measure whose Radon-Nicotian derivative with respect to Gaussian measure is the reciprocal of the Lebesgue measure. So if we assume the function is called G, so what we need to do is that we need to prove that G equals the reciprocal of the function f here. And then everything just follows the same idea from the third results. And here, Runchang will introduce some other definitions in order to before going to the fifth and sixth results.
So thanks to Joy. And here are some more definitions about the Gaussian random variable. So given two measurable space, Okay, so basically for any random variable, it's actually a function sending the mapping the value from the probability space to the real number, extended non-negative real number. And but before, if you look carefully at our definition of the Gaussian measure, it's actually a measure from the R and the big integrable, the big measurable sets to extended non-negative real number. And we want to connect these things together. And a natural definition that connects two measurable space is a push-forward measure. So given two measurable spaces, x1 sigma 1, x2 sigma 2, a measurable mapping from x1 to x2 and a measure from sigma 1 to extended non-negative real number, the push-forward measure of the mu of the measure on the former measurable space is defined to be the measure given by f star mu here. And for any set B in the sigma 2 algebra is defined as the equation, as what's given the equation. Okay, and then with this definition, with the definition of push forward, we can formally define what is a Gaussian random variable. Gaussian random variable, of course, as any random variable, is a function from the the sample space or the set of the measurable space to the real number is Gaussian with the mean parameter and variance parameter, and it is said to be Gaussian if its push forward measure of the probability measure on the probability space is the Gaussian measure. For example, if we say, like in our probability class or statistic class, so given a random variable for its normal distribution or Gaussian distribution, what is the probability that the x equals to or just x in some interval, right? For example, 0 to 1, x in the interval 0 to 1. It's actually the measure of the the measure of the set sigma omega that such that x omega map equals to some value in the interval 0 and 1, right? So basically, it's a given a measure from the probability space to a real number, and if the push forward measure of the given measure is the Gaussian measure, then the random variable, the function, is said to be Gaussian. Okay. All right, and that's with these two definitions, we can go to our fifth important result. That is sum of the standard Gaussian random variable and constant function. So basically, it's a degenerate Gaussian case with variance 0 is it's a Gaussian random variable with the mean parameter mu. So basically, previously, two parameters are 0 and 1, and plus a constant function. The sum of them is a Gaussian random variable with parameter mu and 1. Yeah, that's it. So, well, again, most of the difficulties are like what we did previously. So something about integration, and the new difficult things in these results is just to prove something about the push forward measure. You need to prove that the push forward equals when the function, the push forward of the sum of the function equals to the sum of the push forward of functions. Kind of complicated here, sorry. Okay, and the sixth definition is basically so previous result is dealing with the standard case to non-standard in the mean parameter, and the sixth important result is a standard case to non-standard in variance parameter, and that's it. But you know, as our definition, we define the Gaussian random variable in two cases. The first is that if the variance parameter equals to 0, then it's a defect measure, and if the Gaussian random variable with parameter variance parameter non-zero, then it's just a usual Gaussian. You know, the measure that that radon-Nicolet derivative is a Gaussian function. That's it. And the seventh important result is just basically the combination of the first and you know, the previous two, the fifth and sixth important result. Change. So basically, it's from the non-standard case back to the standard case plus something, and goes back to the non-standard case. And in this sense, we can use our previous result, like result 5 and 6. Okay. Yeah.
Okay, so now comes to the ChatGPT part. So we all know that ChatGPT is now a very popular AI recently. So we would like to try and see if ChatGPT can help us with some link proofs. So here represents the improvement of ChatGPT 4 compared to ChatGPT 3.5. So all the green bars here indicates the improvement or in compared to the ChatGPT 3.5. So actually, in common words, ChatGPT 4 is much better when we wanted to do something related to math. So here's some code provided by ChatGPT 3.5 about Gaussian mesh, and we really got some errors here, like they are all red. We've got some import errors, and actually, okay, so we opened something, but we didn't end it. And actually, ChatGPT will always assume that we have some theorems. They assume that we have proved some theorems in Ling, but actually we haven't do it in Ling. So we've got a lot of errors. And although we still get still get many errors in ChatGPT 4's code, we can have an understanding that they really improve the structures, and just it looks more reasonable, but still lots of errors. So I think ChatGPT 4 can maybe help us with some logic or just give some intuition, but we cannot rely on ChatGPT 4 to do some link codes. And actually, there's no import errors because the import things are written by me and Runchang. It's not written by ChatGPT 4. Still many import errors. Yeah. So I think that's all. That's the end of the presentation, and we want to thank everyone who has listened to this presentation, and we will show special thanks to our supervisors, Professor Kevin Buzzard, who has a great passion for Ling for 5 years, I think, and Jason K. White for his enthusiastic assistance in addressing the issues we encountered. So every time we face some difficulties, we just turn to Mr. Jason and ask him for some help. And also everyone in the Zena Discord channel, because if the difficulties we face are not relative to measures, they can help us with some basic logics in Ling or some improvement in Ling. Yeah, thank you, everyone.